this is Roble. I wanted to give you this video recording so that we could cover material that was from a previous chapter that would be part of this thermodynamics unit test. So we're going to revisit equilibrium, and notice we're going to tie it in with something new, which we call Gibbs free energy. Now, Gibbs free energy, it actually harkens back to the steam engine. They were looking at what kind of useful work can be done with the system. And notice that they were measuring Gibbs free energy to determine if it would proceed in a different or a certain direction, and that tended to be less than zero. So what we need to figure out is whether or not the Gibbs free energy is positive or negative. Now, if it happens to be zero, notice that the system or the reaction is no longer doing any work. So it is at equilibrium. Now, please remember this is a dynamic process that both the forward and the reverse reaction are happening at the same time. The only difference is that the changes in concentration don't take place anymore. So this is how we're going to relate equilibrium with delta G. So in this reaction here, notice that the energy of reactant A is higher than the energy of reactant B. And as a result of it, when we subtract the two, notice that we get a negative value. Now, if you look at the bottom here, we have concentration of A, 100%, and concentration of B, the product, 100%. Because this reaction is thermodynamically favored, eventually it's going to reach equilibrium. And remember, I said that this is a dynamic process, that we have a forward reaction occurring at the same time as a reverse reaction. However, notice that there is more product than there is reactant. So what does that mean? So here we have a situation where we could come from the opposite direction, where delta G is essentially still favored because the difference between B and equilibrium is negative, and as a result of it, we could have product forming some reactant if we started off with pure product. So what does this mean? This means that products are favored when delta G is negative, and we remember from equilibrium constants that the concentration of the products is higher than the concentration of the reactants, therefore the number is greater than 1. We could go from pure product or pure reactant and eventually reach the equilibrium, and that should be where no work can be done, or G is 0. Please remember that this is an example of an exergonic reaction, therefore energy is given off. Now we could have the opposite situation here. Notice that your Gibbs energy of C is lower than Gibbs energy of D, and as a result of it, when you subtract the two, you get a positive value. Now notice that you still get the ski slope on either side, because the energy of C is higher than equilibrium, it's thermodynamically favored. And in this situation, we've got pure reactants here and we've got pure products here. When we reach equilibrium, notice that the concentration of C is higher than the concentration of D. So what does that mean? That means that in this reaction, and this is the opposite of exergonic, this is endergonic, so it's taking in energy. And this situation, it favors the reactants, so the concentration of the reactants is going to be higher than the product. Now, once again, you could shift things in the direction that you want by removing products in order to get more products. Okay, in this slide, I just want to show you that you need to remember that when you have equilibrium, Gibbs energy is no longer positive or negative, it is 0. Therefore, no useful work can be done. Okay, now you may see the degree symbol next to the Gibbs Energy symbol, and what that means is we're talking about standard state. So for standard state, if we're talking about a gas, we're talking about 1 atmospheres. If you're talking about a liquid, we're talking about 1 molarity. And any substance at standard state would have a temperature of 298 Kelvin. Now, occasionally, people will report Gibbs free energy at non-standard state, and when they do that, they typically use the T in the bottom right just to designate that. Now, please remember that when we're talking about Gibbs free energy at standard state, we're talking about 100% of the reactants in their standard state becoming 100% product in their standard states. And they're measuring the amount of work that can be done for that system. Okay, now you may have problems where you need to use this formula. Now notice that they're relating it to equilibrium constant. So we're talking about Gibbs free energy at standard state, and it has to be joules per mole. Notice that we have the R value, which is the gas law constant, okay, and that's joules per mole Kelvin. Temperature must be in Kelvin. Now, this second equation will not be given to you. You should be able to convert the first equation into the second equation. Now, we could estimate using K equilibrium. So this is the second equation that was on that last slide. We can assume that standard state, we're talking about 298 Kelvin, and if we multiply R, which is approximately 8, times 300, we would get about 2400 joules per mole. Now, when we're looking at 2400 joules per mole, if we assume that delta G is significantly higher than 2400 joules per mole, we can assume that equilibrium constant should be significantly smaller than 1. So this would favor the reactants as opposed to the products. Now, you could assume that if it's between 2400 joules per mole or negative 2400 joules per mole for Gibbs free energy, you could assume that equilibrium constant is approximately 1. Approximately. Or if you want, you could assume if Gibbs free energy is significantly smaller than negative 2400 joules per mole, therefore, the equilibrium constant must be significantly greater than 1, which means that products are favored. So this is my last slide where I'm looking at Gibbs free energy and how it relates to equilibrium constant. So notice when we're talking about less than 0, I'm sorry, greater than 0, the equilibrium constant will be less than 1, and as a result, most of the reactants will be favored. And they give you an example here that if you have a number that's close to a positive 20 kilojoules, which is approximately around that 2400 joules per mole, notice that the equilibrium constant will be significantly smaller than 1, and it will be primarily reactants. Lastly, if we have a negative Gibbs energy, we can assume that the equilibrium constant is greater than 1. Therefore, the combination of reactants and products should be mostly products. And once again, if we compare it to that negative 2400 kilojoules, or I'm sorry, negative 2400 joules, if we said negative 20 kilojoules, we would say it's significantly greater than 1, and it should be primarily products.